Woohoo! Welcome back. Godzilla and I are here to discuss P.4 Rational Exponents. And we're going to start right off with a horrible note, which is actually going to make things a lot better. So, this quote says, assume no radicands, that's the stuff inside a radical, were formed by raising negative numbers to even powers. Means that you don't need to include absolute values in your answers. So this is actually going to make things a little easier. But basically, if you try to take the square root of x squared, you don't just get x, because you don't know whether x went in as a positive or a negative. And so this causes a lot of problems. And this note says, let's not worry about it. So let's just agree we're not going to stress about it right now. But what we will stress about is trying to come up with a way to express square roots or radicals as exponents. So this is basically the way it was approached. Whenever a mathematician is thinking, I wonder if I can do something, the first thing they do is say, well, let's assume I can do it. It's a really wonderful way of looking at the world. So let's assume that the square root of 4 or radical 4 can be written as a power of 4. So in other words, square root of 4 or radical 4 equals 4 raised to the power of a, whatever a is. And we say for some value of a, which we need to find. So that's what we're going to do. We're just going to start off and say, let's say these two things are equal. Then let's just play with both sides until we get something we can, get some information from. So, yes, I know, it's very exciting. Godzilla's excited. I'm excited. So what do we generally do when we've got the square root of something? We're going to square both sides. So I've got the square root of 4 or radical 4. I'm going to square it. And I'm also going to square over on the right-hand side. So it's 4a, 4 raised to the power a squared. Okay, so on the left, what is radical 4 squared? Or the square root of 4 squared? Well, you can either look at it as 2, which is then squared, or you can look at it that the square root and the square undo each other. So the 4 is just left by itself. So we've got 4 on the left side. And then we've got this expression that we don't know much about, 4 raised to the power a, and the whole thing's going to be squared. And then we realize, wait a minute, if I've got a power a inside, and a power of 2 outside, what do? I multiply. And so this then becomes a times 2, which is just 2a. So my new exponent is 2a. So 4 must equal 4 raised to the 2/8 power. Okay, but 4 is also just 4 raised to the first power. So if we've got 4 raised to the first power equals 4 raised to the 2 times 8th power, then it must be true, dun dun dun, that 1 equals 2a. Does that make sense? The power over on the left has to equal the power over on the right, since the bases are equal. Woohoo, yay, this is very exciting, woohoo. I'm not sure exactly when this was first figured out, but I imagine that we're probably celebrating, sometime between when the dinosaurs were around and yesterday. So yay, okay, big party. And now we come back and we say, okay, if 1 equals 2a, if I divide both sides by 2, then I end up with a must be 1/2, which is really surprising if you've never studied rational exponents. Remember, rational numbers are fractions. Not all rational numbers look like fractions, but basically that's what we're talking about in this chapter. So in other words, the square root of 4 or radical 4 equals 4 raised to the 1/2. And again, this is very surprising if you haven't studied this before. So again, I will make the note that if this is really brand new, or if this is something you remember from the past, but it's been a really long time since you studied it, please reach out to me or to the tutors. We can give you lots of practice problems. We can answer your questions. We can have a whole rational exponents party, party down like however they would have whenever it is that they came up with this initially, which I wish I knew, but I do not. Okay. So, we've got some other examples. Following this same reasoning, which I'm not going to go through for each of these, but I'm just going to give you these as examples, we can also see that radical x to the 7th equals x to the 7 halves. So let's think about what this means. So the 7, that power of x, that goes there on top. So the 7 is on top. Where did the 2 come from? Remember that a square root, this guy, gives us that 2. And so we see that the power of whatever's inside, so in the radicand, ends up going on top. And the index of the radical, the number that goes in here, so this is a square root, goes in the denominator. Okay, so cube root of 4, the index is 3, is 4 to the 1/3. Now, why is it 1/3? It's because 4 is raised to the first power. So, in other words, the cube root of 4 to the first equals 4 to the 1/3. So this number goes on top, the index goes on the bottom. Okay, let's do another one. X squared, and then we're going to take the cube root. Well, that's just x raised to the 2/3 power. It was x squared, so 2 goes on top. The index, and again, I'll write index in case you did not know this name, this word, or perhaps you just forgot it. Now here with the square root, where's the 2? And the answer is, well, a square root equals this. We just don't write in the 2. So if you don't see a number that's written out for the index, that means it's a square root. Okay, now, and then you know how I love this. This escalated quickly. Let's look at this one because there's a lot going on in this problem. At first, it just looks like blah, 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 blah. But in fact, it's actually not too bad. Let's look at the x. X is raised to the 3rd power. So we see x with that 3rd power there. But the index is 7. This is the 7th root. So down in the denominator, I see 7. So the exponent for x is 3/7. 3/7. The exponent for y, since there's just a y by itself, it's y to the 1st. So it's 1. And then again, it's also the 7th power, or 7th, sorry, the 7th root. Or 7 is the index, so that's y to the 1/7. And then 4, remember, if you're in the denominator, you've got the 1 because it's 4 to the 1st power. You've got the 7 because that's the index, but you also have a negative, right? That negative, that tells us that 4 to the 1/7 is in the denominator of the fraction. Okay, so we've got a lot of denominators running around. We've got numbers which exist. This is all part of the base in the denominator, but then we also have a numerator and a denominator for the exponent. So again, if you're looking at this and your eyes are just spinning in circles, please come talk to me or talk to a tutor. So, and then go ahead and pause this if you just want to give it time to soak in. I'm going to go ahead. I will wait for you for as long as you like. Just pause the video, and as soon as you're ready, we'll start up with the problems. Woohoo! Ready? Cool. Okay, so let's start with some examples. So the first question that comes up is, can we still use all the same rules we had in the previous section? And the answer is yes, of course. So if I have matching bases, so both of these have a base of 5, and I'm multiplying, then remember the rule is you're going to add the exponents. And I know you're all very excited. You're all like, oh, yay, we get to add fractions. I know. the party just does not end when it comes to math. So let's go ahead and figure out, oh my goodness, 5 to what power? So if we're going to add 1/4 plus 1/8, we need a common denominator. Oh joy, I know everyone loves common denominators. So when we look at 4 and 8, remember that we're looking for a larger number that fits both of them. They both go into the number 8. So I'm going to go ahead and write 1/4 as eighths. So here's my red pen of destiny. If I multiply by 2 in the denominator, I get 8. So I multiply by 2 up top. Remember that balance in fractions is top to bottom rather than left to right in equations. So fractions, we got to do the same thing on top and on the bottom. So I multiply by 2, top and bottom, and I get 2/8. 1/4 equals 2/8. So I've got 2/8 plus 1/8. That gives me 3/8. And so I have this as my new exponent. Now, there's something interesting happening here because this is the 4th root of 5. This is the 8th root of 5. And we're saying that this is going to be the 8th root of 5 cubed. So there's some really interesting algebra happening here. But right now, all we're doing is just manipulating the exponents. Woohoo! Okay, let's try some more. I know, I hear you all clamoring, let's do some more. Give us some really hard ones. And I'm like, okay, let's do it. Here's another one. I know these are great problems. If you ever find yourself talking to someone and they're like, what do you do? They're in college and you say, well, I would love to show you, but I don't really feel like it. And they're like, no, we insist. You just pull out this problem and they will stop asking. Guaranteed. They just will never ask you again. They'll be like, oh no. So what do we have here? I'm going to write this one a little bit bigger because it's kind of hard to read. You've got 8, which is the base, raised to the 7/11ths, all over 8 raised to the -2/11ths. Now, we're happy because the two bases match. And if the two bases match, that means we're able to combine them. Now, remember, the rule is that when we're multiplying these two expressions, we add the exponents. In this case, we are going to subtract because we're dividing. And remember that the way we do it is we start with, I'm going to start with the 7/11ths. So I'm going to start with 7/11 and I'm going to subtract. And this one gets a little bit exciting. I know, but this is pre-calculus. So there's, no punches are being pulled at this point. We are just getting in and doing it no matter how gruesome. I'm going to subtract this exponent down here, the -2/11ths. So I get 8 to the 7/11ths minus a negative. I get to do it. Are you guys excited? I don't have my Bat Brothers here, so I'm just going to have to do it with my hands. 2 minuses, ta-da, makes a plus. Woohoo. So 7/11ths plus 2/11ths is equal 8 to the 9/11ths. I know, this is exciting, but by the end of this problem, guaranteed, whoever was asking you to tell them about your math, unless they are a math teacher, has probably fallen asleep or wandered into another room or changed their address and will never speak to you again. Oops, sorry. Did you guys get a chance to see that? Woohoo. Okay, but it's not so bad, right? With practice, hopefully this starts to get a little less weird. Okay, for number 3, we have a base of 27. It's inside parentheses with an exponent of -2/3. And right outside the parentheses, we've got an exponent of 3/2. And remember that when the setup is like this, you've got one base with 2 exponents, one inside, one outside. What do? You got it. You multiply. So I've got 27 raised to the -2/3 times 3/2. So I multiply those two. Remember, again, let me flip back to the first page. If you have 2 bases, each with its own exponent, then you add the exponents. If you've got a single base, just that 27, and 2 exponents, then you're going to multiply those two. Okay, so I've got 27, and here, this is so cool. The math here works the same way. You can actually cancel these fractions. I know, it seems a little bit weird, but these behave, even though they are exponents, they behave just like regular fractions. So, for example, the 3 here and the 3 here cancel. And the 2 here, sorry, I left the ones, the 2 here and the -2 here cancel and leave a -1. So we actually have 1 over 27 to the first power, which is 1 over 27. Isn't that cool? It's so cool. Okay. Yeah, I hear you clamoring for more. Dun, dun, dun. So this one, if the instructions are to simplify, what can I do to simplify? Well, there are a couple things that we can consider. So for this particular problem, 2 raised to the 5/3, there's nothing to multiply or divide or add or subtract or anything like that. But we can actually look at what's happening with this problem. So let's take a look. I can rewrite it. And here's the problem is, although fractions are very convenient for doing algebra, and I know not everyone will agree, but trust me, they are, it's hard to actually see what's happening. Like an exponent of 5/3, a lot of people don't really think about, like, what does that actually mean? So sometimes the best plan is to go ahead and rewrite it in radical form. So this is exponent form. I'm going to rewrite it as the cube root of 2 to the 5th. Okay, so that's the cube root of 2 written multiplied times itself 5 times. And as soon as we see that, we realize that we have a situation for square bear. And I'm looking for square bear, and it seems that I found square bear. Just a minute, let me pull him out. Here's square bear. Arr! Okay, here's square bear. I know, it's truly carnivore theater now. Godzilla and square bear are actually good friends. See the claws? That's a high 5 for carnivores right there. Okay, so what happens with square bear? So if you're going to simplify radicals, you probably know how you were taught to simplify, but this is the way that I teach a lot of classes to simplify radicals. And that is, if you've got a cube root, that means this is not square bear. This is actually cube bear. Okay, so cube bear. Rah. And all of these 2's are trapped inside a cabin in the woods. And it turns out the Wi-Fi has gone out. No more Wi-Fi. Sad, sad pandas. And so they all need to escape. The problem is there's a bear right outside. Arr, he's going to eat everybody. However, there is a really terrible, terrible joke. You may want to put your fingers in your ears briefly for me to tell this joke. Okay, so I'll wave my hands when I'm done. So the question is, if Cube Bear is chasing you and your friends in the forest, do you have to be faster than the bear? And the answer is no. You only have to be faster than your friends. Okay, come back if you put your fingers in your ears. Okay, terrible, terrible joke. That's kind of a dad joke right there, or a math teacher joke. So basically what happens is, if you're talking about the cube root of a really large number, a bunch of 2's multiplied, what you're going to do is you're going to take groups of 3 of matching things. So like there's 3 2's right there, because the index is 3. And these 3 2's are going to go running through the forest. And then Cube Bear comes, and it eats all but one of them. So only 1 2 makes it out. Now, what about these 2 2's that are sitting in there? Well, they don't have enough of them to go running. So there's no chance that they would survive. So they just wait until someone sends help. And I do have a video of where I actually go through multiple examples, and you can always ask me. Also, this is not a traditional way of doing radicals. There are a lot of folks who have much more reasonable mathy ways of doing this. This is just, I think, more fun, plus you get to growl a lot. And so you take groups of 3 if the index is 3, and for every group of 3 you get 1 2 out. And so then what I write is that this is going to be 2 times the cube root of 2 times 2 is 4. And this is a way of simplifying radicals. Basically, the rule is if you've got any groups of factors that are in a number greater than the index, greater than or equal to the index, you have to kind of squeeze them out to simplify. This is something called simplest radical form. And I'm not sure that this is anybody's favorite part of math, but it is an important one. So if this is something where you're like, what the what? I have never heard of this before, you may want to pause and then talk to me, talk to tutors. Let's make sure it makes sense to you. Because basically the rule is we want to all agree what is the best form. If I ask you to simplify something, what should you write as your answer? So that's what governs this. So if anything, like this 2 to the 5th, which is actually 32. What's the cube root of 32? It turns out it's 2 times the cube root of 4, oddly enough. So what about number 5? Number 5 seems very simple. It's similar. I've got the 12th root of a cubed. Okay, awesome. But the problem is that the rule here was if the index is 3, I look for groups of 3. And here, if the index is 12, I only have 3 A's. So the method of using square bear, or in this case 12 bear, that's not going to get us anywhere because we can't simplify. Well, it turns out that this particular one is a case where it actually works better to write it in exponent form. So let's write it in exponent form. So I'm going to write here a little note that I'm going to say that can't simplify. Now, this is one of those times when I am lying. I am lying. I am a liarson here. You can simplify this, but my guess is that a lot of you don't have the experience to know that you can. So I'm going to say you can't simplify, and maybe I'll write easily. There. So let's rewrite it in exponent form. So the base is a. It's basically a cubed, and then the denominator is 12. And you'll remember that a few minutes ago, I told you that fractions as exponents still act like fractions. They're just fractions. They're not magical special fractions, although that would be probably terrifying. They're just regular fractions. So how do you deal with 3 over 12? Well, the number 3 over 12, that's 3 over, let's see, 12. I can reduce that. 3 goes into 3 once, and it goes into 12 4 times. So actually that's going to be a to the 1/4, which is the 4th root of a. Now, can you look at the 12 and the 3 and realize that you could cancel the 3 into the 12 and end up with the 4th root? Yes. Some people are really good at this. I am not one of those people. I would always convert it to exponent form, reduce, and then rewrite it as a radical. And that brings up an interesting point. This problem was written as a radical, so we get an answer as a radical. I realized that up here, I actually should have gone to one more step. And because I answered as a radical, even though the question was asked with exponents. So what I should have done, and I'm going to go ahead and do right now, is I'm going to rewrite this as 2 times 4 to the 1/3, which would probably be an answer since that matches the format. To be honest, I would probably accept this one, but just if you're, if you're doing very fancy math in front of fancy people, keeping your answer matching the format of the question makes sense. So again, over here, question as a radical, answer as a radical. Okay, you guys ready? Dun dun dun! We've got 2 more problems, and both of them are math. So what do we do in a case where we've got a lot of stuff going on? And the answer is, if you've got a lot of stuff going on, you just do your best. So for example, this is the cube root of AB, all raised to the 15th power. So in other words, I've got A times B to the 1/3, and that is raised to the 15th power, right? That cube root becomes a 1/3. And remember that if I've got a base, even if it's complicated like A times B, then I take that, the first exponent, and can multiply it times the second exponent. So in other words, what I've got is AB to the 1/3 times 15, which is AB to the 1/3 times 15 over 1. Now, some people are like, why did you have to go through that step? But the answer is, you don't. I do. It helps me. If it doesn't help you, don't do it. It's just a little extra step that makes the canceling make more sense. And so I get AB to the 5th power. Now, how you should write this is not obvious. I think this is written in both radical and exponent form, so you pretty much can't go wrong. But I would like to point out that this is A to the 5th times B to the 5th, so either one of these would be an acceptable answer, I think. I think this one's prettier, but make sure you also understand that the 5 gets given out to both A and B. Okay, this is very exciting. Dun, dun, dun. We're on the last problem. Oh, man, this is a bear of a problem. See what I did there? It's a bear of a problem. It's a Godzilla of a problem. Okay. Okay, so what should I do when I've got all of these shenanigans going on? And the answer is write really big and go very slowly. Don't let the panic overtake you. So I've got x to the negative 1/3 times y to the 2/5, all raised to the 1/4. And so basically the rule is when you've got 2 things multiplied inside parentheses and an exponent outside, you give out the exponent to each of the factors inside. So in other words, what I get here is x to the negative 1/3 raised to the 1/4 times y to the 2/5 to the 1/4. And then all I need to do here is then realize that in this case I just have to multiply these two, and in this case I just have to multiply these two. So I get x negative 1/3, oh my goodness, I can't write 1/3, times 1/4. Oh my goodness, I don't know what happened to that 3. It's a little bit late, I've been doing too much math. This happens sometimes. And then this one is going to be y to the 2/5 times 1/4. Woohoo. Okay, so that 1/3, seriously, I apologize. I don't know what it is about 3s. I'm just not drawing them very well today. So if I'm going to multiply negative 1/3 times 1/4, remember multiply across the top. I've got negative 1 in the top and 12 in the denominator. Here I've got y to the 2 times 1, which is 2, all over 5 times 4 is 20. Oh my goodness. Maybe I could have been easier on myself if I noticed that the 2 and the 4 reduced. You can cancel. Again, fractions are still fractions, even as exponents. Or if you didn't notice it, you can just cancel right here. And then I get x to the negative 1/12 times y to the 1/10. Now, as far as the answer is concerned, this is correct, but I just want to, since this is our last problem, I want to go ahead and write it out in radical form. So the x is in the denominator because of the negative, and it's x to the 1st power and it's the 12th root. So 12th root of x. Up top, because this is positive, it's the 10th root of y. Bam! There we have it. So, for Square Bear and Godzilla, congratulations. You guys made it. You did awesome. You're amazing. It's been about 30 minutes, so if you've watched this straight through, make sure you go outside, look at something green, take a break, rest your eyes, get some good hydration, get a good snack, maybe some art or some dancing or some music, maybe a little bit of video games, but not too much. And then come back, and I will see you in the next section. Woohoo! Yay! Math on.